Hello everyone, welcome to the fourth online lecture for ME 5030. This will be the lecture for Thursday, April 2nd, and let us look at the plan for today's lecture. We are going to continue some of the things that we saw in the previous lecture, which is the pendulum and the cart problem. Okay, so plan for today. Is we will continue with the pendulum cart problem, and we will complete it. Okay, this is our first thing on the agenda for today, and the second thing is we will have a very nice easy introduction to Lagrange multipliers. Okay, so an easy introduction to Lagrange multipliers. Okay, and Lagrange multipliers, this will be done by means of an example. Okay, so Lagrange multipliers, this will be done via a simple example. And the basic idea is Lagrange multipliers will allow us to handle systems. Suppose if you are interested in constraints, or if you have non-holonomic systems, then Lagrange multipliers is the way to go. Okay, so I just want to make a brief note of that. This enables us to handle non-holonomic systems and also suppose we want to compute one of the constraint forces, we want the normal force at some point, then we can use the Lagrange multipliers. Okay, so obtain the forces of constraint. All right, so that's the plan for today. All right, and let's go back to the pendulum cart problem. We looked at a lot of the aspects of this problem in the last lecture. I'll just very briefly go over what we have seen, and then we will continue onwards from there. Okay, all right, so the pendulum cart problem. So problem from last time. From online lecture 3, continued from online lecture 3. Okay, this is the pendulum cart problem. And I'll draw the figure for this problem in a minute, but I just want to list some of the things that we wanted to obtain in this problem. Our aim here was to obtain the equation of motion, equations of motion, and this pendulum cart system, this was having a lot of non-conservative forces applied on it. Okay, there were non-conservative forces or torques applied, and our aim is how to handle these kinds of things. Okay, we wanted to know how to handle these kinds of non-conservative forces and torques. All right, so let me come back and paste the problem from before. I think I hope that this entire page fits it. Let's see. Okay, so this is what we had from the last time. I just want to pull that and then bring that here, and let me see if all of it is fitting within one page. So probably not. I just want to move this up a little more, and let us now see. All right, so I have to do a little more of an adjustment here. Okay, so we have the pendulum system, maybe reduce the size of that a little bit, and then I want to ensure that everything fits in. All right, so here we have from the previous lecture the pendulum and the cart. Okay, there are several things going on. There is first of all, and let me use the magenta color to highlight some of these things. um, there is the force F1 of t which is applied here. This is a non-conservative force. Okay, then we have the damping element here, which also acts as a non-conservative force. Okay, so this is another one. So this is also non-conservative. Okay, then we have the kinetic friction between the cart and the ground. That is also another non-conservative force, so I just want to point that out as well. Then I have the torque that is applied, m of t, that is a non-conservative torque, and then I have the force F2 of t, which is a non-conservative force as well, so in a different color. So here is another non-conservative. Conservative, and then m of t is going to be a non-conservative torque. Okay, all right, so these are the things that were acting on the body, and what we did in the previous lecture was we obtained the kinetic energy of the system. mc is the mass of the cart, mp is the mass of the pendulum. There were two generalized coordinates in this problem, which was x and theta. As you can see, that x dot square is the velocity of the square of the velocity of the cart, and then the combination of theta and x dot, theta dot, and so on, that will give you the velocity of the pendulum. So for details of these, please refer back to online lecture 3. We were also able to derive the potential energy of the system, so that was fairly straightforward. Okay, and what I want to do now is I just want to start listing what are all the non-conservative forces. I want to use the coordinate frame setup outside the problem in the form of a stationary observer, and then write these forces in the proper manner. Okay, and for that I need my figure again, so I'm going to copy that figure only. Okay, so I'm going to take some of these. Well, I can do the following. So I'm going to paste my figure from before. Okay, so here is the figure from before, and I'm going to cut out some of these details which are not necessary for us. All right, okay, I'm going to cut that out, and then even in this figure itself, I'm going to clear up some of these things which are probably not very useful for us. Okay, so we already know that's a cart. We also know that, okay, there is kinetic friction taking place there. Yes, I'm going to cut that out. Then we know for sure this is an applied torque, so we don't need any of those details. All right, and then in this problem, I have the spring force applied. The spring force is a conservative force, which is why this is not included in the QJ NC terms. Okay, so that's something that you want to keep a note of. Okay, the spring force here is a conservative force, and this was included in the expression for the potential energy. All right, and I want to scoot this up a little bit. I'm sorry, scoot this figure onto the side a little bit. Okay, so here is the problem as such. And what I want to do next is I want to set up a coordinate frame, and let's say that the coordinate frame is set up such that the x-axis has the unit vector ex, the y-axis has a unit vector ey, and so on and so forth. And I need to choose an origin for this coordinate frame, and to do that, let me actually look at drawing the figure again, but looking at only the non-conservative forces on the body. Okay, so the non-conservative forces that are of importance to us are this one here, this force F1, then there is going to be the force of friction, then these forces here, and then also the force of friction. If I draw the force of friction, it's going to be opposite to the direction of motion of the cart, right? And so this is going to be F mu, okay, the kinetic friction force here, and That's another non-conservative force. Okay, so what I'm going to do is I'm going to redraw with just the non-conservative forces. Redraw the problem with only the non-conservative forces. Forces and torques. Okay, and so here I have the cart. I'm sorry that I keep redrawing these, but I think it is necessary at this point. Then I bring this creature here and I do the same thing there. I duplicate that and bring it here, and I think we had a different color for this, so let's go with the color that we had. I should have taken care of that earlier itself. Okay, and so this is in blue color. Then I draw the forces that are acting on this body, so I'm going to draw them in the color red. Let me maybe extend this a little more so that everything is equidistant. So this is going to be coming down a little more as well. Now I'm going to have the force F1 of t, which is acting at that particular point, right? So that is F1 of t, and I'm going to call that point where it acts as the point 1. Okay, that's the first force. Then I have the force F2. I have the pendulum first of all, which is attached to the body here, which I'm going to draw in a minute. So here is the pendulum, and let me increase the size of this a little more. Okay, all right, so here is the pendulum, and they are pinned to the cart at the center of the cart, right? And there is a force that is acting on this body, so that force we called as the force F2. It's acting vertically up, F2 of t, and then I'm going to call the point on which that force is acting, I'm going to call that as point 2. This is at some instant in time. Okay, then I'm going to have the third force, which is the damping force. The damping force is also going to try to resist the movement of the cart, right? And then I'm going to call that as F suffix d, and I'm going to say that that is acting at the point labeled 3. Okay, and then here we will list all these forces as well, of course. And then I'm going to have the friction force, which I'm going to say is acting right here at the center of the cart. It's acting somewhere along that surface. It's a traction force, of course, but we will say that, okay, but for convenience, the friction force is acting in the following manner at that particular point. Okay, this is going to be F mu k. Okay, and then this point I'm going to call as point 4. All right, and then I'm going to do one more thing. I'm going to say that, okay, the box or the cart has some dimensions. Here are the dimensions of the cart. Okay, so I'm going to say, okay, the total height is 2h, and the width of the cart is 2b. So starting from here to there, I will say that this is little h and little h. Okay, and these are dimensions, so let's put them in dotted lines. Okay, and likewise I'm going to have the width of the cart as well. So I'm going to say that, okay, starting from here all the way down to here, and then of course not drawn as a square, but you can assume it to be a square. Okay, this is going to be little b, and this is also going to be little b. Okay, and dimensions once again, so we will draw them in dotted lines. All right, and then we have to have a coordinate frame, and we say that, okay, the coordinate frame can be attached anywhere on the body or outside the body. So I'm going to set up a coordinate frame that is outside the body. Let me set it up here. Okay, so here is the y direction. The unit vector in that direction is ey. The unit vector in this direction is ex. Okay, so this is going to be ey, and this unit vector is going to be x, and this is a stationary observer denoted by the point O. And we're going to say that the total distance, and I think we call this as point P here, okay, and then the center of mass of this rigid bar we call as little g, right? And then we will say that the distance from the point O all the way to the point P is going to be a distance x, which is x of t, right? This is the distance that is varying over time, and it's one of our generalized coordinates as well. So I'm going to mark that distance now, okay. I'm going to mark that in the blue color as well. And so all the way from here to there along the x direction is a distance x of t, and let's draw that in dotted lines. All right, so we have everything set up now. What I'm going to do is I'm going to start listing these forces in terms of how they are written vectorially, okay. So let's make a list of all these forces, and we will keep going back and forth to the figure that we have on the top there, okay. So list of all the forces, of all the non-conservative forces, as vectors, okay. All right. The first force I'm going to write is the force F1. This force F1 of t could be some function of time, so could be like a sinusoidal excitation force or something. This is acting in the positive x direction, so this is Ex of t times f of t. So the first is F1 of t is going to be written as a vector, so this is going to be the magnitude times Ex, okay. Then the second force which I'm going to write is the force F2, which is acting vertically up, okay. So if I have to write that as a vector, this is going to be this is F1 by the way, F2 of t, and then this is going to be in the Ey direction, okay. And then one thing I missed out on drawing on this figure is the torque that is applied on the pendulum, okay. So that is the m of t, which is the applied torque. So we need to keep a track of that as well, because that's also a non-conservative quantity. Then I'm going to write the damping force, okay. That's going to be Fd. So Fd is the damping force, and this acts to oppose the direction of the velocity of the cart, okay. So for us Fd is going to be minus c times x dot times Ex, okay. The damping force, as you might have seen probably from a class in system dynamics or something, okay. The damping force expression is from system dynamics or some other basic systems classes, okay. The expression for Fd obtained or taught in system dynamics all right. So this is the third force, and then the fourth one is going to be the force of friction, which we say is acting at the point labeled as 4, okay. This is going to be F mu k is going to be minus F mu k times the sine of the velocity in the Ex direction, okay. Here Sgn represents the sine, is the sine of the velocity of the cart. All right, and we can say that F mu k is mu k times n. So if you want, we can also say that F mu k is going to be minus mu k times the normal force times the sine of the velocity vector in the Ex direction, And lastly, we have the applied torque, okay, which we're going to be calling as m of t. If I write it as a vector, you can quite easily see that the torque applied is in the counterclockwise direction. So the unit vector that is going to be representative here is the vector coming out of the page, which is the EZ vector. Okay, so m of t written as a vector is going to be m of t times EZ, where EX cross EY gives you EZ, and m of t is in the counterclockwise direction. M of t is the applied torque, m of t is in the counterclockwise direction. All right. Now, among these forces and torques, we said that last time, the last lecture, we can differentiate, or we can kind of divide these forces, non-conservative forces, into velocity dependent and velocity independent forces, right? And the same goes for torques as well. So from last class, I just want to rewrite that expression. Okay, so from last lecture, the total non-conservative forces and torques for the jth generalized coordinate can be written as follows. Okay, we have Qj non-conservative is, first of all, Qj non-conservative forces plus Qj non-conservative due to the torque. Okay, and Qj non-conservative forces itself can be broken into two pieces. Qj non-conservative is Qj non-conservative forces, and we said this was velocity dependent. I just want to come up with a notation so as to write it quickly. Qj non-conservative forces, this is velocity independent, and then Qj non-conservative torque. Okay, this is velocity dependent, so Vd means velocity dependent, then Vi means velocity independent, and this is the torque. Okay, now an important thing that we need to keep in mind is, okay, in our setup, what are the velocity dependent and the velocity independent forces? So for us, okay, the velocity independent forces are the following. Are f1 of t, which is f1 of t times ex, and then f2 of t, which is f2 of t times ey. Okay, these are the velocity independent forces. Okay, then we have the velocity dependent forces. Friction force and the damping force is a velocity dependent force. Okay, so that's going to be fd, which is minus c x dot. As you see, there is a velocity term coming in there, times the ex, and then f mu k, which is going to be minus mu k times n times the sine of the velocity vector. Okay, and then we have the torque, the applied torque. applied or non-conservative torque, that is m of t is in the counterclockwise direction. Alright, so these are the things that we have for us. Now what we need to write is also the following. Okay, we need to write the position vector of these points that we had chosen as 1, 2, 3 and then 4 in our figure. So if I go back to our figure, and I'll come back to these forces again, so we need to write the position vectors for these different points that we've chosen, which means that I have to probably bring this figure once again onto the next page where we're going to write all these things down. So just to rehash, we have the velocity independent forces, these are the VI's, then we have the VD's, and then we have the applied non-conservative torque. Okay, then what we need to do is the following. We need to next to write the position vector Ri from a stationary observer to the points on the body where the forces are acting. Okay, let me just write that out clearly, where the forces are acting. That was still not very clear to me. Okay, where the forces are acting, and these are labeled as points 1, 2, 3 and 4 on the figure below. And this is the same figure that we had from some time back in solving this problem. Okay, so I'm going to bring that figure here, and then you'll see that we need to write the position vector Ri from the point O to where all these forces are acting. So we essentially need the position vector from point O to point 1, point 2, point 3 and point 4. Okay, so I'm going to list them as the following. Okay, let's start off with the first one. Okay, so the first one is R1. This is going to be from point O all the way to point 1, so that's going to be x of t plus little b. There is no y distance because the origin is coincident in terms of the y location at the point P. So this is going to be x of t plus some b in the ex direction. Then I'm going to have R2, which is going to be the position vector from the point O. Okay, so if you want, you can write this as R1 slash O. This is R2 slash O. Okay, this is from the point O to where the point 2 is acting. So here I have to first travel horizontally, and then I have to travel down, and then by a certain distance as well. Okay, so if I set that up here very quickly, and then I have this distance here. I know the total length is L by 2 and L by 2, which is L. So this angle here is going to be theta. Okay, so this distance is going to be L times sine theta. L times sine theta, and the height is going to be L cos theta. So if I write R2, this is going to be x plus L sine theta in the Ex, and then minus, because I'm going down below the negative below the positive y-axis, so minus L cos theta Ey. Okay, so that's done. Then I write the third position vector, which is R3, 3/O. This is going to be from point O to point 4, okay, where we say that approximately this is where the friction force, the kinetic friction force, is acting. So from point O to point 4, here is I'm sorry, I have to write it from point O to point 3, apologies. So this is where the damping force is acting, okay. So that's going to be x of t minus b ex, and then we can sneak up and write R4 as the following. R4/O is going to be where the point 4 is acting, so that's going to be x of t in the ex direction minus some constant height h ey. Okay, so that's going to be the situation here. All right, and I just want to make a note that this is a constant, and a little b here is also a constant. All right, so we have all these listed, and then we have all the forces acting as well. So we have pretty much all the ingredients that are needed for writing out the non-conservative forces, the qj's for each of the generalized coordinate. I just want to make sure that I'm writing these a little properly here. So I just want to move that out. Let me just rewrite this expression here. Okay, apologies for that. So this is going to be x of t in the ex minus h in the ey, so many meters or whatever. Okay, all right, now we come back to writing what our qj's are. Okay, so qj non-conservative, okay, this is going to be the three things that we wrote. Qj non-conservative for the velocity dependent forces, then qj non-conservative for the velocity independent forces, and then qj non-conservative for the torque. Right, and from a common expression that we looked at in the last class, this is going to be, if you have a velocity dependent, then you're going to have the time derivative of the jth generalized coordinate present. So this is going to be summation of all the velocity dependent forces. Okay, and let's say that the summation is over some index I, so this is fi dotted with dri by dqj dot. Then this is going to be summation over a different index. I said this was an index m. If you want, this is going to be fvi, okay, m dotted with drm by dqj, and then lastly sum of all the torques that are acting on this body, summation over all the, let's say, n m of n dotted with d omega n by dqj dot. Okay, so this corresponds to that term here. So let's just draw a corresponding arrow to these things. Okay, so these correspond to that. Then I'm going to have the other correspondences as well, velocity independent, and then the torques. This corresponds to that, and then lastly I'm going to have this correspondence here. All right, so now we come to the onerous task of actually writing these out for our problem. Okay, so for our problem we're going to have how many generalized coordinates? We're going to have two of them, which means that we have to write it for x and we have to write it for theta as well. Okay, and then we have the potential energy, the kinetic energy, and all these other factors that are going to come into play, and then we will eventually have to write the Lagrangian, combining everything out. All right, so for our problem, okay, our problem, we have two generalized coordinates. Okay, and our generalized coordinates are x and theta. Okay, so this is x of t and theta of t. Okay, these are our generalized coordinates. And how many velocity dependent forces we have? We have two of them, right? And then we have two velocity independent forces, and then we have one applied torque. Okay, so here is what I'm going to be doing. I'm going to be writing the qj for each one of these generalized coordinates as follows. Okay, so starting from qx non-conservative, this is the total non-conservative effect on generalized coordinate x, and then likewise we're going to say q theta non-conservative is the total non-conservative effect on generalized coordinate theta. All right, so now let's start listing everything out. Okay, so qx and c is going to be the following. Okay, f1 is a velocity independent, f2 is a velocity independent, f3 and f4, which is our fd and f mu k, are velocity dependent, and then I have the m as well, which is an applied torque. So here is what I'm going to do. Okay, so this is going to be, first of all, f1 of t dotted with dr1 by dq, or in this case this is going to be dx. Okay, then I'm going to have f2 of t dotted with dr2 by dx once again, and I'm going to have two more. Okay, I'm just going to sneak and write these out a little closer so that I can label them as I go. And then I have fd, which is a velocity dependent, so this is going to be dr3 dot by dx dot. Okay, that is important, and I think I missed out on writing the dot here. Apologies for that. Okay, I'm sorry, not in the velocity independent, velocity dependent. It's going to be here. Okay, and then lastly I have the fourth one, which is f mu k dotted with dr4 dot by dx dot. And lastly, okay, I'm going to have the following. So these are all the forces which are acting. Okay, plus I'm going to have m of t dotted with d omega of the cart by dx dot. Okay, this is the entire set of forces, non-conservative forces and torques that are acting with respect to the generalized coordinate x. Okay, where we say that omega c is angular velocity of the cart, which obviously is going to be 0. Okay, that's something to keep in mind. And so here you will see that these two terms put together are your velocity independent. Okay, these two terms here are velocity dependent. And this term is due to the applied torque. Okay, angular velocity of the cart, of course, is going to be 0 because this cart is in pure translation. And likewise, I'm going to write the same thing for the theta generalized coordinate as well. So q nc theta, I'm sorry, q theta nc is going to be f1 of t dotted with dr1 by d theta. Then f2 of t dotted with dr2 by d theta. Okay, then I'm going to have fd dotted with dr f3 dot by d theta dot. Then I'm going to have f4 or f mu k, I'm sorry, this is f mu k dotted with dr4 dot by d theta dot, and then lastly m dotted with d omega of the pendulum, which is given as the subscript p, divided by d theta dot. And likewise, as before, these two terms are the velocity independent, this is the velocity dependent. Okay, so this is velocity independent and this is velocity dependent. And you see that this is quite laborious, right? This is not fairly straightforward or anything, but this is the best way you can handle these kinds of non-conservative forces. They're quite messy, but we don't have any other recourse. So let us do the following. We're going to bring in all these f1, f2, f3 and f4 from above, and r1, r2, r3 and r4, and then we just do the differentiations with respect to each of them. Okay, so let me start off in the next page. Okay, these are the forces. So we shall now calculate all of these. Okay, so I start off by looking at the force F1. So F1 of t. Okay, so I look at F1 dotted with dr1 by dx1. This is going to be F1 ex dotted with I'm sorry, this is dx, not dx1. Okay, this is going to be r1, which was the following. So this is going to be d by dx of x of t plus b ex. Okay, and you will see that here b is a constant, so this is just going to be d by dx of x of t, which is 1. So this essentially gives me f1 ex dotted with ex, which implies that f1 dotted with dr1 by dx is equal to f1. Okay, so that's the first piece of good news for us. Okay, so let me highlight that by putting a box around it. Okay, and you will immediately see that the next situation is going to be slightly more easier. So if I look at f1 dotted with dr1 by d theta, this is going to be f1 e of x dotted with d by d theta of x of t plus b ex. There is no theta in this term, which means that this is going to be completely 0, which implies that f1 dotted with dr1 by d theta is equal to 0. Okay, this was as expected. The force F1 is acting on the cart, so you're obviously not going to see it influencing the pendulum directly, at least. Okay, so that's one thing. Then I go to the same force F2 and I keep doing this for the rest of the forces as well. Okay, so if I do this for the force F2, okay, so F2 of t. Okay, so I look at f2 of t dotted with dr1 by dx. This is going to be f2 ey dotted with d by dx of x of t plus b ex, which is going to give me the following. This is f2 ey dotted with ex, which is 0. Okay, so f2 of t dotted with dr1 by dx is equal to 0. This is once again not a surprise because the force F2 is acting on the pendulum, and so this is obviously not going to directly affect the cart. Okay, then I have the other one, f2 of t dotted with dr1 by d theta. I'm sorry, this has to be r2. My apologies for that. I think I have to go back and change this entire thing. So let me get rid of all of this. Okay, my apologies. So if I do that, I start off with a clean slate. Okay, so f2 dotted with dr2 by dx. Okay, this is going to be the following. So this is f2 ey dotted with d by dx of the following. This is x of t plus something in the ex and then something in the ey. That's what we had for r2. X plus L cos theta ex minus L sin theta. I'm sorry, this was cos theta and sin theta were flipped. So this is actually going to be sin theta. L sin theta ex minus L cos theta ey. And obviously this gives you the following. f2 ey dotted with, you will see that the term containing x is the one that's going to be coming out, multiplied by ex, dot product with ex, which is equal to 0. So this is obvious. f2 dotted with dr2 by dx is equal to 0. Once again, no surprises here. Okay, all right, and I keep doing the same thing. f2 dotted with dr2 by d theta. Okay, now this is interesting. This will come out to be f2 ey dotted with d by d theta of x plus L sin theta ex minus L cos theta ey. Obviously I'm interested in only the ey term, so this is going to be fe 2 ey dotted with L sin theta will be L cos theta ex plus L sin theta ey, and this is essentially going to be f2 times L times sin theta. Okay, and so we have f2 dotted with dr2 by d theta is f2 times L times sin theta. So we say that this is a generalized force, but this looks more like a generalized moment. So when we say generalized force, it could mean either a moment or a force. Okay, that's something to think of. So this is a moment. Okay, so when we say generalized force, it could mean a force or a moment. Something to keep in mind. Okay, and we have other things going on. Now I look at the third one. So this is the damping force Fd. Okay, so if I look at Fd dotted with now dr3 dot by dx dot, this is going to be minus c times x dot ex dot product with d by dx dot of r3 dot, which means that I have to take the time derivative of r3. So I just want to make a note. R3 is x minus b ex, which means that R3 dot is going to be x dot ex. So this is going to be x dot ex. If I do the dot product, this will end up giving me fd dot to the dr3 dot by dx dot is minus c x dot. And you can immediately see that whatever we have the forces that are acting on the cart, they remain as forces, the generalized forces, but then the forces acting on the pendulum, they turn out to be actually generalized moments. Okay, and then I want to make a quick note here and say that, okay, fd dotted with dr3 dot by d theta dot is equal to minus cx dot ex dotted with d by d theta dot of x dot ex, which is obviously 0. So fd dotted with dr3 dot by d theta dot is 0. Okay, this was expected. The damping force is going to affect only the motion of the cart. Of course, the motion of the cart directly has an impact on the motion of the pendulum, so there is only an indirect consequence. And then we come to the kinetic friction force. So F mu k. Once again, the basic idea is the same. F mu k dot with dr4 dot by dx dot is minus mu k times n times sine of the velocity vector in the ex direction. And then a note quickly, r4 was the following. It was x ex minus h ey, which means that r4 dot is x dot ex. So this is dotted with d by dx dot of x dot ex, and as expected, f mu k dotted with dr4 dot by dx dot is going to give me minus mu k times n times sine of x dot. Okay, so this once again comes out to be a force acting on the cart, because the cart is in pure translation, so we are seeing only the forces that are affecting it. And very quickly, f mu k dotted with dr4 dot by d theta dot is going to turn out to be 0 minus mu k times n sine of the velocity vector dotted with d by d theta dot of x dot ex, which is obviously 0. So f mu k dotted with dr4 by d theta dot is 0, and there's a dot on top of the r4. Alright, so we are almost getting to the end of this problem, and for the sake of convenience, I'll just list out what are the steps to be taken, and then I'll not complete the entire problem in terms of the differentiations and so on. I'll just leave that as an exercise for you. I'll post it on my more elaborate lecture notes on Karman. Okay, the last one is the moment m of t. This is fairly straightforward. M of t dotted with d omega cart by dx dot is 0. This is because omega cart is 0. The cart is in pure translation. Okay, and then that's A. Then I have B, m of t dotted with d omega of the pendulum by d theta dot is going to be m of t e z dotted with d by d theta dot. If you look at the angular velocity of the pendulum, it's theta dot in the ez direction, right? Which means that this is just going to give me m of t directly applied as a moment. So I have two pieces of information from here. One is that the applied moment is not affecting the cart directly, which is quite obvious because the applied moment is acting on the pendulum. And the other thing is this quantity m dot omega of the pendulum d theta dot is going to end up being m of t. Okay, all right, and so we are ready with our list of all these forces. Okay, and once we have this, then we can say the following: qx non-conservative. Okay, if you go back to our expression. Okay, if I go back to Qx non-conservative from here, let me maybe pull that down, and we can kind of get rid of some of these quantities and so on. Okay, so if I pull that out here, let me get rid of this. Excuse me. And then I paste that, and then I see, okay, let me get rid of some of these terms here. We know what they mean by now. Okay, likewise here, and likewise here too. I'm sorry. Alright, so we can now say the following. First of all, this entire term is going to be 0, as you see from before, okay, which implies that Qx non-conservative, if I make use of all the expressions that we have seen, f1 dotted with dr1 by dx, that just gave me f1 of t. Okay, then f2 dotted with dr2 by dx, that term ended up being 0 for us. That was not acting on the pendulum, not on the cart. Then I had fd and f mu k, so that's going to be minus cx dot, and then minus mu k times n times sine of x dot. Right. Alright, and I just want to make sure that everything is taken care of here in terms of these friction forces and so on. Okay, and the other thing we have to write out is okay, q theta. If I pull out the expression for q theta from here, okay, I bring that down here, I copy that, and then bring it down, and we can see that several terms are gotten rid of in this. I'm going to remove these. We know what they are by now. Okay, and so the first thing that I'm going to get rid of is, okay, f1 is not going to act on there, fd is not going to affect our situation, f mu k is not going to affect us, which essentially means that q theta nc is going to be f2 times L sine theta plus m of t. And so if I collate all our results together, okay, so combining all our results or collecting all results, I have qx and c from here. Okay, so I copy that and I bring that down here. Then I have q theta nc from here. I copy that and I bring that down here. So that's one and two things. Then if I go back to the beginning of the problem, I have my potential and kinetic energies as well. So I'm going to bring those fellows as well down here. Okay, so I'm going to take all of these, my potential and kinetic energies, and then bring them down here. Okay, because we now need to write the Lagrange formulation. Okay, so I paste that here, and I can get rid of some of these terms. Okay, so I remove that. I've screwed this up a little more higher up. Okay, and so we are now ready to write everything that makes sense for us from the point of view of the Lagrange formulation. Okay, so I just want to put a box here. This is an important term. Okay, all right, and so we can now write the Lagrange equations. I'm sorry, I should have put these back on. For some reason, kind of missed out. Okay, all right. Now we write the Lagrange equations. So using the kinetic and potential energies, I can write the Lagrangian L. Okay, so let me first write that. So L is T minus V. So that's going to be half mc plus m pendulum x dot square, and then half mp l cos theta x dot theta dot plus 1 by 6 mp l square theta dot square, and then I'm going to have minus half kx square plus mpg l by 2 cos theta. Okay, so this is the Lagrangian, and then we have two equations of motion. And with your permission, I'll very quickly write these things out. Okay, so the first one is d by dt of dl by dx dot is dl by dx plus qj non-conservative. Second thing is d by dt of dl by d theta dot is dl by d theta, and instead of writing qj here, I should be writing this is qx, I'm sorry, and this is q theta non-conservative. And let's go ahead and do these things very quickly. I'll scoot up and bring the Lagrangian down here, okay, so that I need it for my differentiations. Okay, so I copy that and I bring that here. All right, so I go to the first one. First one, I have d by dt of dl by dx dot. I'm just going to do this very quickly. So this is x dot, term containing is mc plus mp, so this is going to be mc plus mp x dot square becomes x dot. Then I have a term containing theta here, that's going to be plus mp l by 2 cos theta times theta dot, that's a term containing x dot. Okay, these are the only terms containing x dot. This is equal to dl by dx. There is only one term containing x, which is the potential energy term here, so that's going to be minus kx, and then I'm going to have all the non-conservative forces, that is f1 of t minus cx dot, and then minus mu k times n times sine of x dot, which is the friction force. Okay, all right, and if I rewrite this and have the first equation of motion, then I get the following. Okay, so the first equation of motion, I have to do the time derivative of the term inside the bracket there, so that's going to be mc plus mp x double dot. Then I'm going to have the time derivative of theta dot, so that's going to be mp l by 2 cos theta double dot, time derivative of cos theta, so chain rule, minus mp l by 2 sine theta dot square, because I already had a theta dot there. This is equal to minus kx minus cx dot plus f of t minus mu k times n times sine of x dot. Okay, so this is the first equation of motion. Then the second equation of motion, for that we have to consider d by dt of dl by d theta dot is dl by d theta, and then q theta non-conservative. And so this is going to be d by dt of, if I go back to the Lagrangian here, I considered the terms containing theta dot. There's a term containing theta dot here, which is going to be mpl cos theta x dot by 2. Okay, then there is a term containing a theta dot square, so that's going to be mp l square times 2 times theta dot, and then I have a factor of 6 which means that it's going to be 3, so that's going to be plus mp L by 3 theta dot. That's about the term containing theta dots, and then I have some terms containing theta. I have to be careful here. Okay, if I go back to the Lagrangian, there is a term containing theta which has both the x dot and the theta dot, so that's going to be a sine theta, negative sine theta term, so that's going to be minus half mp sine theta x dot theta dot, so that's one term there. Then I'm going to have mg L by 2 cos theta becomes minus mg L by 2 sine theta. Okay, and that's minus mp g L by 2 sine theta. And then I have q theta non-conservative as well, which is going to be plus f2 L sine theta plus m of t. Okay, simplify. The second equation of motion is the following. I have a couple of simplifications. I have skipped a step or two here. One step that I have skipped is you have mp L by 2 cos theta times x dot. If I differentiate the cos theta, I get a minus sine theta, and theta dot and x dot, I have a similar term there. On the other side, they vanish. So I'm going to have the following. Okay, mp L theta double dot by 3. Then I think there should be an L square term there. I think I forgot to bring the L square, so this is L square, I'm sorry. Okay, I also missed out on writing the L square, not there. I guess that's not the term containing the L square, that's only in the theta equation, so this is mp L square. Okay, so mp L square theta double dot by 3, then I'm going to have plus mp L by 2 cos theta x double dot. Okay, that's another term there, and this is equal to, these are all the terms on the left hand side from the time derivative, then minus mp g L by 2 sine theta f2L sine theta plus m of t. And as I mentioned, the term here, this will cancel off. I just want to make a note. Okay, this term will cancel off when we take d by dt of mp L by 2 cos theta x dot. Okay, that is from here. All right, so these are the two equations of motion. This is a fairly formidable problem. I mean, it's kind of nasty in the way you have all these forces acting on it. So here is the first equation of motion. So this is a coupled differential equation, and of course solutions will be nicer to see if one actually simulates these problems. Okay, and I have some plans for helping you simulate some of these things in MATLAB, and I'll outline those plans towards the beginning of next week. Okay, in the form of a separate set of lectures. All right, so we are now going to move on to the idea of Lagrange multipliers. So these are the two equations of motion. We're done with this problem, so we're now going to move on. Okay, move on to the idea of Lagrange multipliers. Okay, all right, and Lagrange multipliers typically enables us to handle non-holonomic systems, or enables us to find the force of constraint. Okay, so this will help us handle non-holonomic systems, and also, if needed, enables us to obtain the force of constraint. Okay, so those are the two things that are of use to us, and obviously we have to look at non-holonomic systems in the coming lectures, so we need the idea of Lagrange multipliers. Now the derivation for this, we are going to not do it in this particular lecture. I'll be posting that on Carmen. Okay, so the derivation or the idea of Lagrange multipliers will be posted on Carmen. We just want to make use of Lagrange multipliers as a tool for solving problems. Okay, so our aim is to make use of this as a tool for solving problems. I'm going to start off with a very simple problem. Okay, so this is very silly, and you will see that this is too trivial to use the Lagrangian method, but it kind of pushes the point for us. Okay, I'm going to consider a block, smooth block on a horizontal surface. Okay, so consider a smooth block sliding on a smooth horizontal surface. Right, and this essentially means that we do not have any friction, so we are neglecting friction. Okay, and we are saying that the block is moving due to initial conditions. Okay, so what are our assumptions? Friction is negligible. Kinetic is negligible. And the second thing is we say that okay, this block is translating horizontally on and due to initial conditions only. Okay, so no external or applied forces. The block starts motion due to initial conditions only. Okay, so I'm going to draw the block. Okay, so here is the block. On a smooth horizontal ground. I'm going to draw the ground in a minute. Okay, so here is the ground. And I'm going to say that okay, this is the center of the block. Okay, I'm going to set up a coordinate frame. So let's say that the coordinate frame that I'm setting up is as follows. Okay, let me pull that a little to the side here. Okay, so here is the coordinate frame that I have. So this is going to be the EX unit vector. This is the EY unit vector. This is the point O. Okay, and let me say that the height of the block is some constant value h. Okay, or 2h if you want. Okay, so let's say that the height is 2h. Okay, and let's say the mass of the block is little m. So mass of the block little m. Now there is only 1 degree of freedom in this problem. I'm not going to go into the details of this. This is too trivial for us, but we know that this is a 1 degree of freedom system. Okay, what are the constraints? We are looking at a planar problem. And the constraint is that if I say the height h is a constant, right? So y is equal to h is a constant. So if I call this as let's say that instead of calling it as ex and ey, if I call that as a little x and little y, then y is a constant. So I'm just going to draw y here, okay, is equal to h. Okay, so y is equal to h, which means that the system is holonomic. These are all holonomic constraints. So all constraints are holonomic, which means the system is a holonomic system. So what is the big deal in this problem? I mean, what is our aim? Okay, our aim is to use Lagrange multipliers and obtain the normal force of contact between the block and the ground. Okay, and to do this we will very quickly digress into the Newtonian mechanics idea, and then we'll come back to the Lagrange idea. Okay, so basic thing is there is only one degree of freedom here. The degree of freedom I'm going to say is the variable x. Okay, that's the generalized coordinate, so x of t is the degree of freedom. And x of t is starting from the center of the block, going this way, is x of t. Okay, all right, so for us the generalized coordinate is x of t. Okay, but if I want, I can say the configuration coordinate is actually x and then y, and the constraint is y is h, and so this is why we have x of t as the generalized coordinate. Okay, all right, so this is the configuration coordinate. I just want to, all right, and so I digress back to Newtonian mechanics. So from Newtonian mechanics, if I draw the free body diagram and the kinetic diagram of the block, okay, so let me do that very quickly. Okay, so I have the block. Okay, so here is the block, and I'm going to take the same block and copy that, and I'm unable to get it, but let's do this here. Draw two blocks. Okay, free body diagram and kinetic diagram. That's for the free body, this is for the kinetic diagram. Okay, so free body diagram. This is the kinetic diagram, and we essentially see that, okay, in the free body diagram, the forces acting are the weight of the block, which is acting vertically down. This is going to be m times g. Here is the normal force of contact. Okay, and then on the kinetic diagram, the only force that is going to be acting is mass times acceleration, so that is m times x double dot. Okay, let me write the x carefully. M times x double dot. All right, so equation of motion is mx double dot is equal to 0, right? That's the equation of motion, and the constraint equation we get is N is equal to mg. So this is from Newtonian mechanics. Newton's second law. Now, how do we do the same thing using the Lagrangian? How do I get the normal force to be equal to mg? Here is how I do it. Now, to use the Lagrange formalism, okay, we do a couple of different things. I'm going to do this a little quickly, but then we will come back in the next lecture and solve a problem much more elaborately. Okay, we first look at the configuration coordinates. These are x of t, y of t, right? So they help locate the center of the block. Okay, so that's one thing. Then the second thing we write is, okay, what is the constraint equation? This is y of t is equal to h, right? This is a holonomic constraint. So here is what I'm going to say. Now say that q1 is x of t, q2 is y of t, which means that the constraint is going to be q2 is equal to h, which means I want to write this in the Pfaffian form. Is if I differentiate this, first of all, dq2 by dt is d by dt of h, which is 0. That is the first thing, which means that if I cross multiply and write the Pfaffian form, of the constraint, the Pfaffian form is going to be 0 times dq1 plus 1 times dq2 is equal to 0. An important thing to note, okay, J is the constraint equation number, and then I is going to be the index on the configuration coordinate. Okay, which means that if I compare this with our typical way of writing the Pfaffian form, so the standard Pfaffian form is summation I aji dqi ajt dt is equal to 0 for ours. Our Pfaffian is going to be the following, right? It's going to be 0 times dq1, 1 times dq2 is equal to 0. So if I write this in our regular form, so you can call this as a11 dq1, a12 dq2 is equal to 0, which means that dq a11 is equal to 0 and then a12 is equal to 1, right? This is for j is equal to 1 and I is equal to 1 and 2, right? J is the first constraint equation. There's only one constraint equation for us, okay? J represents once again, j is equal to 1 means only one constraint equation, okay, and I is equal to 1 and 2. So I can say that a11 is 0, a12 is equal to 1. Okay, all right. So now with all of this, we are going to say the following. We are going to write the Lagrangian formulation or the formalism using the configuration coordinate rather than the generalized coordinate, okay, to obtain the constraints constraint force, we write the Lagrangian formalism using configuration coordinates. That is very important to realize. Okay, so we now say the following. We introduce a multiplier and this multiplier is going to be called as lambda. Okay, and here is the Lagrangian formalism with the multiplier. Okay, for the ith configuration coordinate, and for j is equal to 1 to m number of constraint equations, m number of constraint equations, we have d by dt of dl by dqi dot is equal to dl by dqi plus summation j is equal to 1 to m lambda j a ji plus qi and c. Okay, this is the most general formalism to calculate constraint forces or for non-holonomic systems. Right, we can do it for that as well, as you will see in the coming lectures. So let's go ahead and do it for our problem. Okay, so I'm going to bring back our figure from before. Okay, this is the same silly figure that we drew some time back. Okay, I'm going to take this guy and bring it back down. Okay, so I'm going to copy this and I'm going to paste that here. Okay, now we can say that if I call this point as the point P, okay, velocity of point P is x dot ex plus y dot ey, which means that velocity of P square is x dot square plus y dot square, where this is written in terms of the configuration coordinates. Excuse me. Okay, this is written in terms of the configuration coordinates, which means that if I write the kinetic energy, which means that T is equal to half m Vp square, so T is half m x dot square y dot square, and we said x is q1, y is q2, right, which means that the kinetic energy is half m q1 dot square q2 dot square. Now potential energy is m times g times h. Okay, this is by making use of the horizontal line here as the datum, so I'm going to choose this line as the datum. Okay, and you see that the height h is the height of the point P, the center of mass of the block, from the datum. But instead of writing it this way, I'm going to write it in the following manner. This I'm going to say is mg times q2. This is because y is equal to h, which means that q2 is equal to h. So write both the potential energy and the kinetic energy in terms of the configuration coordinates. That is the first key step. Okay, so I'm just going to put a box on top of around these two, okay, so that we can call them back again when needed. And I want to finish this problem. I appreciate your patience in sitting and listening to some of my long lectures here. Okay, so once I have that, then I also notice that there is qx non-conservative is 0, qy non-conservative is 0, which means that q1 non-conservative is 0, q2 non-conservative is 0. There are no applied or external forces or torques. Okay, that's one thing that we can say. Then I have the following. I have the constraint equation. In the Pfaffian form is 0 dq1, 1 times dq2 is 0. Just want to rewrite that again. And so this tells me that a11 is 0, a12 is 1. Okay, this is for j is equal to 1, I is equal to 1 and 2. Now I write the Lagrangian formulation. First one, for x or q1, I is equal to 1, right? We have d by dt, dl by dq1 is equal to q1 dot. Okay, this is q1 dot. I just want to make a note of that. That's q1 dot here. That's dl by dq1 plus q1 nc summation j is equal to 1 to 1, because I have only 1. This is going to be a j1 times lambda 1. Okay, lambda j a j1. Okay, then for y or q2, I have I is equal to 2, so d by dt dl by dq2 dot is dl by dq2 plus qnc q2 summation j is equal to 1 to 1 lambda j a j2, right, because I is equal to 2. Okay, so then I take these equations and I say, okay, Lagrangian L is T minus V, which is half m q1 dot square q2 dot square minus mg q2. Then the constraint is q2 is equal to h or q2 dot is equal to 0. Do not substitute this into L now. Okay, do not substitute this into the Lagrangian now. Okay, then I take the I is equal to 1 equation. Okay, so I is equal to 1 or the x equation. If I do the differentiations, right, I have d by dt of dl by dq1 dot. So there is only one term containing q1 dot, and so this is going to be m times q1 dot This is equal to dl by dq1. There are no terms containing q1, so 0, plus no terms containing the non-conservative forces, so I can cancel off some of these. So this term will be gone, that term will also be gone in our problem, so that's also 0, plus, so I'm going to write this as plus a1 times lambda 1, where lambda 1 is the first Lagrange multiplier. Okay, and then what do I see? For I is equal to 2, so I'm going to call this as equation 1. Okay, then I see I is equal to 2, or the y equation, d by dt of m times q2 dot. Okay, because there is a term containing q2 here. dl by dq2 is actually minus mg plus 0, right, plus lambda 1, I'm going to write that in the red color, okay, as I've done in the previous step, plus lambda 1 a12, right. This is the term containing, this is for q2 nc, this is q1 nc, okay, and this is equation 2 for me. Now substitute q2 dot is equal to 0. From 1, what do I get? I get m times q1 double dot is equal to 0. This is because a11 is 0 from above, so that term is gone for me. Okay, so if I draw that in the blue color, so this term is now gone for me. Okay, then, and I just want to make a note, a11 is equal to 0 from Paffian. Okay, then from 2, something really nice happens. I see that q2 dot is equal to 0, which means that this term is now going to vanish completely. Okay, this is after substituting q2 dot is equal to 0. Okay, that's q2 dot there. And here is what I end up getting. I get 0 is equal to minus mg plus lambda 1 times a12, which is 1. Okay, and here I want to make a note and show that, you know, a12 is equal to 1 from above, or the Paffian. Okay, a12 is equal to 1 from the Paffian, which tells me essentially that lambda 1 is equal to mg, and this is the normal force. So the lambda 1 multiplier, I did not know what this multiplier stood for initially, but then I know that this is now the normal force, which means that lambda 1 is the Lagrange multiplier, stands for the normal force. And we know that this is a normal force from Newton's mechanics laws, Newton's law that we applied earlier in the problem. And we know that lambda 1 is equal to mg is the normal force of constraint from having obtained n is equal to mg from Newton's laws earlier. So kind of a shady thing here is that, you know, we don't know what this lambda 1 is to begin with, but then we have to deduce. Okay, so that is one disadvantage of the Lagrange multiplier method. So I just want to make a very quick note. we have to deduce what lambda 1 means. So as you see here, one thing that you can make a note of is, okay, suppose I have to find constraints, and perhaps the Newtonian way of solving problems is a better idea. Okay, next class we will solve more problems. Thank you very much for your patience and time. Okay, you're all, I hope, doing safe and staying safe and staying healthy, and of course hopefully going through the lecture notes that I'm posting. If you have any questions, please feel free to talk to me by email or by Carmen Zoom. Okay, thank you very much and take care.